Hello, in this video we're going to examine the definition of a vector space and apply this definition to some more abstract vector spaces than we have in the past. So recall that a definition of a vector space is that we've got a set V, and V consists of elements called vectors for which there are two binary operations, namely addition and scalar multiplication. We've got several axioms that must hold, and I'm going to number these so that we can refer to them easily later on. The first property or axiom is that vectors coming from V, they have this closure under addition property. Similarly, we've got closure under scalar multiplication, and we should note that that C is an element coming from the real numbers. And so sometimes you will see the notation C is an element of the real numbers. We have addition is commutative, we have addition is associative, there's a zero vector that lives in V. Also, for all vectors in V, we've got additive inverses. With respect to our scalar, we've got distributive properties that hold, we have associative properties that hold, and multiplying any vector u times 1 coming from the scalar field gives you back u. Okay, so the first thing we want to analyze, example 1, is the set of even integers of vector space. So let's let E denote the set of even integers, and the set of even integers looks like elements 2 times n, where n is an integer. And again, if you're a person that likes some of this notation, you can say 2n, where n is an element of the integers. It's a nice way of writing that. All right, so let's check axiom number 1. Is this set closed under addition? So for axiom 1, let's pick a u and v in our set, capital E, and we want to test if u plus v is back in V. So u looks like 2n, and v looks like some other even integer, where n and m are elements of the integers. So we've got two even integers. We'll denote them u and v. And when we add u plus v, we get 2n plus 2m, which is 2 times n plus m. This is just another integer. Call it L or something like that. And so we get the sum is in E. So axiom 1 is satisfied. But when we look at axiom number 2, so let's look at axiom 2, pick C in the real numbers. Now C could be anything. I mean, C could be like, pi or square root of 2, right, or negative a half, whatever it is. And the question is C times u in our set? And the answer is not always. And as a counterexample, you might see something like, square root of 2 times vector u. Here's an even number, even integer. That's certainly not in E. And so this is a set of even integers turns out to be not a vector space, because we failed axiom number 2. Okay, another example you might want to consider would be the set of odd integers. Is that a vector space? And you might be thinking no, for the same reasons that the set of even integers failed. That's certainly going to be the case. We even get that it's not closed under addition. So if you let O be the set of odd integers, which we can represent as 2n plus 1, where n is an integer. And notice if they pick any two odd integers, where n and m are integers, and we add those together, move some of my examples down here a minute, make a little bit more space, notice that we get u plus v, adding up these two quantities, we get 2n plus m plus 1. And this is not in the set of odd integers. So this is actually an even number, and that makes sense. If you had two odd numbers like 3 plus 5, you always get an even, and that's what this proof shows. So again, our conclusion is not a vector space. So we can think of vectors in Rn, but we can think of vector spaces in these more abstract settings. Okay, so let's take a look at an example related to matrices. In this example, we want to consider the set of 2 by 2 matrices with real number entries, and we'll call this M sub 22, M22, the set of matrices that are 2 by 2. Is this a vector space? All right, well, let's go through our axioms. So, for example, axiom 1 asks if it's closed under addition. So let's pick U to be some 2 by 2 matrix, and let's let V to be another 2 by 2 matrix. And when we add these up, U plus V, certainly we do get another 2 by 2 matrix. Okay, so that axiom is verified. Next, let's look at axiom 2. So axiom 2 asks us to analyze the multiplication by a scalar. And so C times U, that would just give us, let me pick a different scalar because we already have a C entry in our matrix. Let's pick alpha. So let's go alpha times vector U. We'll get alpha A, alpha times B, alpha times C, and alpha times D. And that is certainly in our set of 2 by 2 matrices. So I'll say it's in M22. So far we've satisfied axioms 1 and 2. The next axioms, and let me scroll up to the top of the screen here, the next axioms have to do with matrix addition. Is it commutative and is it associative? And the answers are certainly yes, so let's just note that down here, not much to show. So axioms 3 and 4, so verified by properties of matrix addition. And we could certainly go through and show that for these matrices, but it's pretty believable. Axiom 5 asks us, is there a zero vector in the set of 2 by 2 matrices? And certainly there is. We can call that vector. Let me make a little bit more space for us here. We could certainly call that vector the 2 by 2 zero matrix. And that has the properties that we see, right? U plus 0 equals 0 plus U, which equals U. So that axiom number 5 holds. So far we're doing well. We've verified all our axioms. And scroll back up. We've got a couple more to look at. Does every matrix have an additive inverse? That is certainly true. Scalar multiplication, certainly those properties 7, 8, and 9 hold, and those are all to do with properties of scalar multiplication of matrices, and certainly property 10 holds. So we'll just make a note axioms 6 through 10 hold, again by of additive inverses, and scalar multiplication of matrices. So it turns out that this set is a vector space. So we'll say therefore M22 is a vector space. The last item we want to look at for today has to do with a set of real valued functions. So real valued functions, we've been working with those creatures since perhaps calculus and things like that. So let's take a look. We'll define this set as kind of a script f, which I'll write like that. Let's let f be the set of real valued functions. So this is a set of f functions such that f takes in real number inputs and produces a real number output, real valued functions. So let's go through our axioms. Axiom 1. Axiom 1 says pick a u, so we'll call that f of x, and pick another vector, call it v, that'll be some other function, g of x. Is it true that u plus v lives in our set? And to do this, we need to think about what it means to add functions f plus g. And the way we do that is by point-wise addition. So adding up what happens to f at a particular x value and adding that to the coordinate of g evaluated at x, that gives us f plus g of x. And that is certainly in our set of real valued functions. Axiom 2. If you pick any real scalar, so C comes from the set of real numbers, the field of real numbers, notice that C times U is asking us to figure out what C times F does, and I'm going to write that as C times F of X with some parentheses like that. That is the same as what we mean by C times F evaluated at X. To figure that out, it's just evaluate F at X and then multiply by the scalar C. And that is certainly in F. It's not that we have functions that map to the complex numbers all of a sudden. We still are in this land of real valued functions. Okay, some other axioms to verify. So, is it true that u plus v is equal to v plus u? And that is certainly true because you can add functions. The addition of functions is commutative. And we get an associative property, which I won't put down the details. You could check that on your own. Some other things that you might want to ask yourself, what would be the zero vector in this set F? So what is the zero vector in set F? Well, the zero vector would just be the zero function. Right? So a zero would be the function f such that f of x equals 0 for all real numbers x. Okay, and so it's true that if you pick u, I'll call it g of x for a moment, just to keep our letters straight, you could add the zero vector, and to figure out what that does, you'd be looking at adding up what f does to x and what g does to x, and we know that what f does to x, it just gives us 0. And so what we get out here is just the action of g of x hence it's just essentially G. Lastly, I'll kind of skip ahead for some of these. So we've got additive inverses exist, and certainly properties of scalar multiplication, say 7 through 10, can be verified as well.